Figure 4, another illustration of definition 2 is given in Figure 5. The points on the graph of a sub n must lie between the horizontal lines y equals big L plus epsilon and y equals big L minus epsilon if n is greater than big N. This picture must be valid no matter how small epsilon is chosen, but usually a smaller epsilon requires a larger big N. You have Figure 5. If you compare definition 2 with definition 2.6.7, you will see that the only difference between the limit as n approaches infinity of a sub n equals big L and the limit of x approaches infinity of f of x equals big L is that n is required to be an integer. Thus we have the following theorem, which is illustrated by Figure 6. Theorem 3. If the limit of x approaches infinity of f of x equals big L and f of n equals a sub n when n is an integer, then the limit as n approaches infinity of a sub n equals big L. Figure 6. In particular, since we know that the limit of n approaches, the limit as x approaches infinity of 1 over x to the r equals 0 when r is greater than 0, theorem 2.6.5, we have 4, I guess de technically definition 4, the limit as n approaches infinity of 1 over n to the power r equals 0 if r is greater than 0. If a sub n becomes large as n, if a sub n becomes large as n becomes large, we use the notation the limit as n approaches infinity of a sub n equals infinity. The following precise definition is similar to definition 2.6.9. Definition 5. The limit as n approaches infinity of a sub n equals infinity means that for every positive number big M there is an integer big N such that if n is greater than big N, then a sub n is greater than big M. Again, definition 5, the limit as n approaches infinity of a sub n equals infinity means that for every positive number big M, there is an integer big N such that if n is greater than big N, then a sub n is greater than M. If the limit as n approaches infinity of a sub n equals infinity, then the sequence open bracket a sub n close bracket is divergent, but in a special way. We say that open bracket a sub n close bracket diverges to infinity. The limit laws given in section 2.3 also hold for the limits of sequences, and their proofs are similar. Limit laws for sequences. If open bracket a sub n close bracket and open bracket b sub n close bracket are convergent sequences and c is a constant, then the limit as n approaches infinity of open a sub n plus b sub n close equals the limit as n approaches infinity of a sub n plus the limit of n as n approaches infinity of b sub n. And the limit of as n approaches infinity of a sub n minus b sub n has equals the limit of a sub n minus the limit of b sub n, both with as n approaches infinity. And the limit of c times a sub n as n approaches infinity equals c, the limit of 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 c times the limit as a approaches an n as n goes to infinity. Then there's a blank here. The limit of C equals C as n approaches infinity. The limit of A sub n times B sub n as n approaches infinity equals the limit of A sub n times the limit of B sub n, again as n approaches infinity. And the limit of A sub n over B sub n as n approaches infinity equals the limit of A sub n as n approaches infinity over the limit of B sub n as n approaches infinity. If the limit of B sub n as n approaches infinity does not equal 0, the limit of A sub n to the power of p as n approaches infinity equals, open bracket, the limit of A sub n as n approaches infinity, close bracket, to the power of p, if p is greater than 0 and A sub n does not equal 0. Squeeze theorem for sequences. The squeeze theorem can also be adapted for sequences as follows in Figure 7. If A sub n is less than B sub n, which is less than C sub n, for n greater than or equal to, restarting that, if A sub n is less than or equal to B sub n, which is less than or equal to C sub n, for n greater than or equal to n sub 0, and the limit of A sub n as n approaches infinity equals the limit of C sub n as n approaches infinity equals big L, then the limit of B sub n as n approaches infinity equals L. Another useful fact about limits of sequences is given by the following theorem, whose proof is left as exercise 87. Theorem 6. If the limit of the absolute value of n as n approaches infinity equals 0, then the limit of the absolute value of n as n approaches infinity equals 0. See Figure 7, the sequence open bracket B sub n close bracket is squeezed between the sequences open bracket A sub n close bracket and open bracket C sub n close bracket.